Hi. So in this lecture, we're gonna be looking into specialized methods that are designed for solving large-scale optimization problems. So basically, decomposition is a concept, meaning that we are breaking a large-scale problem and solving it as smaller parts that are then recombined. And we'll see that the working principle behind any decomposition problem is that solving a smaller version of the problem over and over is more efficient than trying to solve once the large scale version or a problem that is large scale. So it's the idea that the time taken to solve the problem piles up faster than linear, and that means that you see benefits by. So let me draw a graph to try to explain this better. So suppose this is the time taken to solve our problem, which can be the number of operations we need, computation operations we need to do with a standard measure of computation operation in terms of time. And this is the, try to do something more straight. This is the size of our instance. So this is the size of the problem. And we know that typically solving optimization problems, especially mixed integer programming problems, this is something that behaves like so, or perhaps even more inclined, to make my point a bit easier. Meaning that, you know, as you increase in size, the time taken to solve it increases faster than linear. So basically what we're trying to do is to somehow to recover the capability of having our time scaling like so, because then I suppose I can break a problem that was originally of this size into several problems of a smaller size, say this, and then instead of taking this time, whole time here, you will take this time n times, say 5 times. So it will be somewhere like here, or perhaps somewhere like there. But still, trying to combine the time taken for, when combining the time taken for smaller problems is faster than solving the full space. So that's when decomposition methods will be employed. And there is basically two main ones. Dantzig-Wolfe for column generation, who will talk about the subtle difference between the two, and then Bender's decomposition. The reason I chosen these two is because so Bender's decomposition nowadays is available in commercial solvers. Well, I know of one commercial solver, Cplex, that has an implementation of Bender's decomposition you can use right away out of the box. But Dantzig-Wolfe and column generation, even though I'm not familiar with any commercial implementation of it, there's quite a few open source either implementations of column generation or frameworks that allow you to implement your own column generation. And in terms of you know, research that is really close to have an impact in real world problems, column generation is one of these methods that has been used over and over again to solve important problems. Being vehicle routing and travel salesman problem and the likes, one example. Right. So let's first in this video discuss this notion of decomposition, and how it's gonna play a role. What does it mean to decompose a mathematical programming problem? So basically, the main idea is that we are with this objective of looking into a large problem and breaking into small parts, we'll be in the search of finding how can we remove any linking elements that it might have, such that we can then employ this notion of breaking it into smaller problems. That's what we mean by decomposing the problem. So trying to figure out which is the linking element that prevents us from being able to solve the problem as separate parts. So here is, for example, what we mean by removing linking parts. So suppose we have a problem P, and it's just this maximization problem where we want x to live in the set of x. And turns out that the set X has this interesting structure that is formed by the intersection of a collection of xk's, and where each of these xk's, they define a feasibility region for the components, xk associated with. So notice that this intersection might be a bit weird at first, but it basically means that you have constraints that are involved with the components, for a collection of components of X within this set K, and you don't have any other constraints associated with the other variables. So it means that, it's just kind of like the real valued space for the variables not involved in that component. So when you intersect them all, what you actually get is this stacked separation of the problem. So here, for example, if I have capital K components, my first component, I'll have a number of components of X associated with this first element. And I have my constraints associated with those first components. So this could be a vector. This is a vector with n k elements and 1 element even. So I have these components, and you see I have constraints associated with them, but I don't really have any constraints with this component, say X capital K. So when I intersect them, I only get, this. So you can see that if you think about the structure of this problem as a whole, because whenever I'm looking at this part, there is nothing associated with the other components that I have to take into account. I mean, x1 doesn't show up in any of the other constraints. It means that I can simply break this problem into independent parts, solve them one by one for each k, and then combine them into a single solution. And that's beneficial, especially in the context, that we live now in terms of computational developments with parallel or highly parallel computing being available. Meaning that suppose you have, say, or even in a context where you actually have, doesn't have highly parallel, but you have your own computer with a few 8, 16, 32 threads available. What you can do is that if you can break these into independent parts, you can assign each of the threads to be solving these independently. So instead of taking the time of solving this whole thing, if, the whole time taken to solve the whole problem will be the same as the time it takes to solve the lowest of each of these. So you basically, from P, you assign parts k equals 1 all the way to k equals n to different computing nodes, threads. And once they are all finished, they return for me the solution of P. And suppose that it takes t1, that it takes t2, and that it takes tn seconds. Whatever is the largest of this is the bottleneck. So it will take tn to solve the problem instead of the time it would take to solve P. So when you finally get a separating structure like that, when you have, you can kind of see that this is a problem, that this will be a summation in K, and the set of constraints will be replicated for all K. When that is the case, you have at hand something that is separable or decomposable. And that separability is a holy grail in optimization because of the possibilities for parallelization, which is even better, than the own benefit of solving this in serial and see your time scaling almost linearly, right? It means that instead of having a linear multiplier on the time of one problem, you're actually taking the time to solve one problem. But of course, if that was the case, there wouldn't be such thing as a hard optimization problem or a large-scale optimization problem. And the reason for that is this presence of so-called complicating structures. And they can be basically of two types. The first type is when we have something that is called a complicating constraint. And a complicated constraint, it means that you have this constraint that connects the components across xk. So it means that you have, notice how here these constraints, or even this constraint, only involve the components in k equals 1, and these constraints only involve the components in k x of x in x capital K. But now you have this constraint that actually involves components both from x1 and all the others, including xk. So it links this, suppose that these are all zeros. So I have only something like a1x1 plus akxk equals b. So that would be linking these two subproblems. So this is like in the general form, saying that I could potentially be linking all of them. Okay. So this is what we call complicating constraints. And you see that now I can't really do this trick, because as soon as I try to solve this, I have to know what is the value of x1 such that this constraint can be correctly considered. So I can't really solve them in any sort of sequence. And an equivalent notion is when you have something that is called a complicating variable. So then it means that it's very similar, but now the notion is that you have this variable that shows up not only in its own subproblem, but it also shows up in subproblem somewhere else. So I'm representing it with the extra variable x0 that is showing up here in all subproblems. But it could have been just the same as having something, say, dkx1 here. That would also cause a connection between the subproblem 1 and the subproblem k. So complicating constraint connects the subproblems more or less horizontally, and complicating variables connects them somewhat vertically, but creates a connection across the subproblems. And basically because you have these two types, we have the two types of decomposition methods we are talking about in this lecture. So you have, at your hands tools to deal with either case. So when we are in the setting where we have complicating constraints, so basically what we do is we employ a notion that we use delayed variable generation. So it's kind of funny because you have a complicating constraint, you create a delayed variable generation approach, and then when you have a complicating variable, you employ a delayed constraint generation approach. But this is going to become clear in the coming videos. But basically, the idea is that we use something that is called the Dantzig-Wolfe decomposition, or Dantzig-Wolfe method, to consider basically you consider the constraint on an implicit form using a convex hull, and you little by little, iteration by iteration, generate the required variables until you can prove optimality. So by doing so, you can somehow go around the need to have to consider the problem as a whole, and it allows you to look at them decomposed in the space of case. This is what we're going to be looking in the next video. And similarly, when you have complicated variables, then the strategy is try to separate the structure that has that variable and the structure not possessing, the substructures not possessing that variable. So you end up again with a implicit representation that you can use to separate the problems into k elements. And this is what we're going to see in the third video. And just some important remarks here is that the most important thing is you have to be able to identify what sort of complicating structure you have, because once you can identify what complicating structure you have, then you can choose the most suitable method. And that's part of the art of using these sort of methods to solve challenging problems, is identifying whether you have complicating variables, complicating constraints. More likely is that you have both. And how do you decide whether to use then column generation on your complicating constraints or Bender's decomposition on your complicating variables? That requires experimentation, experience, and is problem dependent, unfortunately. And that's kind of one of the reasons why these methods, they haven't been able to be fully adopted in a larger scale, because it's really hard to generalize them for different problems. So it really require specialist knowledge in order to be able to develop efficient decomposition methods. But there are academic and commercial implementations available. I'll point you out to some in our exercise session. Basically, I know a commercial implementation of Benders that has been available for a few years now for Cplex. And in terms of column generation methods, I know some frameworks that allow you to develop ones. There is a very good one in Julia called columna.jl, and there is a few more out there that I'll show you. All right, I think that's a good stopping point for this video. In the next video, we'll get into the details of Dantzig-Wolfe decomposition and column generation, which happen to be sort of the same thing, but is slightly different. So we'll talk about that. So see you in the next video. Bye-bye.